fly swatters today at Family Dollar Hardware. No, not today, in Delhi, New York. I didn't know there was a Delhi in New York.
It's Delhi. Yeah.
Delhi, okay. Anyhow, and
but we do have very good delis.
So one fellow just took the fly swatters and marked them through the scanner one by one, and they're a dollar a piece, the fly swatters. And the second person counted the number of fly swatters and multiplied that number by one and put it down here. Look, the question I have is, if your students were doing these this way, which one would you say, now, Jake, that's a great way to solve the problem, or are they equivalent? So there. I'll let you mull that over in case things get boring. You could write me a little essay on this problem. A couple of other things I wanted to say. I had mentioned, I think, sometime to my class that I'm working on a project with the Department of Dina Education to have a workshop in the summer that will be a Navajo culture-based workshop on mathematics and science for teachers in the Navajo Nation. And this university, the Department of Mathematics here, has been doing something like that with just the focus on geometry, geometric patterns, and the making of rugs and making of patterns on pottery. And for the past 15 years or so. And if we get this workshop going, I'd like some teachers to come down. So if you have any interest in doing that, please let me know. And if it happens, I'll get back to you and we'll go ahead. It'll be just a one-week workshop at a time that is between classes you teach and classes that you have to take during the summer. So probably the first week of August, something like that. Which, great weather down in the Navajo Nation. Yeah, don't bring your parkas. The other thing is, another project that I'm working on is developing a hybrid online Mathematics 1030 course for concurrent enrollment. Mathematics 1030 is a course that we give in higher ed in the state of Utah that meets what's called a quantitative, or half of the quantitative literacy requirement. It is real-life problem-based applications of mathematical ideas, graphing, algebra, geometry, and so forth, and so on. And it is for people who do not intend to go on to other kinds of mathematics. And we're hoping to get started with that in the fall of 2012. We're looking for teachers who would be interested in teaching such a course. We'll have a workshop on the course materials, how we think a hybrid course should be taught sometime during the summer, and then you'll teach it next year. So if you're interested in that, one member of our group is Tyler Haslam, so you can talk to Tyler about it as well. If you're interested in that, let me know. Yes, Thomas?
My understanding, most concurrent classes require a master's to teach them, but you're addressing people who probably won't have their master's.
We're working on that. Yeah, you won't have your master's by that time, but we're working on that. Those rules are made up by the particular institution of higher ed that makes the agreement, and the part of what we want to do, maybe Diana can speak to this.
She has no idea what
but okay, she doesn't want to. She chooses not to speak, but that will have to be worked out. And that's it. Well, I'm great to see all of you. I want to tell you that Amanda and I are teaching the course, and half of the people are in that course, and the other half are in Amina's course, and then the third half are just people who happen to be walking by, and so this was like a fun idea. And I know you caught me on that third. You missed my 9th lesson. Here.
Oh, darn.
There. One fellow.
Those are your receipts.
Yeah, she.
Yeah, I'll
Vi
follow
Hart-
up on that in a moment
You will.
because I think it is
Okay.
interesting.
Okay. Anyhow, Vi Hart is fast becoming a celebrity with her website, and she does all kinds of exciting mathematics things in exciting ways. And she's moving from New York to the Bay Area in California, and so of course Salt Lake City's between there. Since she was passing through, she decided to spend a couple of days with us, and so now I'm going to give you Vi Hart.
Thank you. All right, first priority, people in the back, we got more room, so come up here right now and fill up this table. And actually, we have more seats here, too. So yeah, I'm Vi Hart. I'm a recreational mathe-musician. My official job title is mathe-musician. The question of the day is, what do you do with 60 fly swatters? You could play the drums. We're going to think about that more later and make something out of them eventually at the end of the day. And if you're bored, I guess the first thing I'm going to do is, talk a lot with the projector, and then we'll play and even maybe migrate out of here to have some more room. So I found it interesting Hugo was talking about the 2 receipts because I wanted to get fly swatters, and then of course I said, hey, these are great, maybe I'll buy another 30 fly swatters. And the first woman had scanned each fly swatter individually, and not just like scanning one 30 times, but each separate fly swatter in the pile, she had to pick up, scan, put it in the bag, pick up the next one, scan it, and that just shows like a fundamental misunderstanding of like equivalency, that people should see that these 2 things like are equivalent in a way, and that's kind of what mathematics is all about. So if our students are better trained in mathematics, maybe she won't have to scan each individual fly swatter. She'll say, all right, I see there's an equivalency between these fly swatters, and I can just like treat them all as the same thing and do a quantity entry in my register.
Explanation, though.
Yeah?
I mean, if you're for simple words at a checkout, you don't get much exercise all day. So this is the only way she gets to exercise her arms.
That's true. Yes, you can work on trying to take the tags off, but we'll probably get to fly swatters kind of later. So another focus, actually, another follow-up on what Hugo was talking about Navajo art and the patterns you find there. One of the things I want to get really deep into today is freeze patterns, and I'm going to show you freeze patterns in music because I like to play with music. But also these patterns you find in all sorts of native art, and categorizing what cultures use which freeze patterns, how often is this really interesting way of looking at why did this culture never use this certain pattern? Or so if you hang out here today and play with freeze patterns, then when you start looking at these patterns in art, you're going to recognize them and say, aha, I know what that pattern is. All right, but let's get started on the talky part. Can we turn off half the lights or kind of be, I don't know, maybe can someone grab those? Yeah. Anyway, so I do these videos on the internet where I draw stuff and people kind of like it. But today I'm going to be talking about more of the physical things I do, because I like to make things. And making things is important because every time you make something out of a different material or in a different way, you learn something different about it. So a dodecahedron is a dodecahedron, right? But when you make a dodecahedron out of a melon like this, I was slicing kind of the planes of the faces of the melon to get the dodecahedron. And in theory, you just toss up your melon, give it 12 cuts with the knife. Those will be the 12 faces, and bam, it will land as a dodecahedron. And if you just get those 12 planar cuts in the right way, you'll end up with this shape. And then, of course, I carved holes in it, and I don't know, it was pretty delicious. And, you can do that with any shape, with any apples are a good carving medium. So this is made out of stained glass. I was playing with stained glass for the first time last month. It was awesome. But here, first I cut out these glass pentagons. And if you put together 3 pentagons, they kind of form this angle here, and they have to. It's like, that's how it works. You put them together and you get that. And if you take 12 pentagons and you put them together, 3 around each corner, you get a dodecahedron. You don't need to understand anything else about the dodecahedron except I cut out 12 pentagons, I tape them together, 3 around each corner, and bam, that's a dodecahedron. But that's like a completely different understanding of it than finding the 12 planes and cutting it. Then there's edges. This is made out of balloons. And here, the thought is, how do I connect up edges to make a dodecahedron? Well, they kind of have these cycles of 5 here, and then you have other cycles of 5 connecting, and 3 edges meet at each corner. And if you do that with your edges, not even thinking about the dodecahedron, you end up getting the dodecahedron. But now you know something else about it. If you make it out of candy, probably you ate a lot of sugar. So that's another thing you can do sometimes. And so those were like pure edge and faces and corners of dodecahedra. This is the symmetry of a dodecahedron made out of lollipops. Hard to tell from the outside, but on the inside, each lollipop stick is carefully woven, and this, what's that, pentagon is like one of the faces of a dodecahedron. And on the candy theme, basically anything you find, you should probably arrange into a Sierpinski triangle if you have a bunch of them. And fractals are great because you just follow a simple rule. And here the rule is, right, we're going to start with 1 candy corn. And the rule is whenever you have exactly 1 candy corn at one of these corner points, you put another candy corn below it. So here, there's a candy corn here, and there's no candy corn here, so that's exactly 1 candy corn goes below it. Here there's not exactly 1 candy corn, there's 0, so 0 candy corns go below it. And here we've got these 2 candy corns together. That's not exactly 1, so 0 candy corn goes below it. So the only rule is where there's exactly 1 candy corn, exactly 1 candy corn goes under it. And that's the only rule you need. And when you just do that, this happens. You get Sierpinski's triangle, and you can keep on going forever. This is a hyperbolic plane made out of balloons. Yeah, hyperbolic planes are great. Here the rule is, you know how if you have like triangles and you want to tile them together, regular triangles, which are called equilateral triangles, they kind of tile 6 around each corner. You can get 6 of them around, and that's flat. You can see floors like that, walls like that. If you try and fit in a 7th and you're using floor tiles, it's not really going to work flat. But if you're using something flexible like balloons, or if you can do this made out of paper, and you just tape 7 triangles around each corner, it's just going to get wobbly, like there's too many triangles, and it's like, what is it doing? It's all over the place. But that's a hyperbolic plane, because flat is one kind of plane. There's different rules here. So if you just follow that one rule of how you're tiling your triangles, it's a regular tiling. And here's pentagons. You can't fit 4 pentagons around flat. So it's to draw it out, you're kind of forced to squish it to fit it all in this diagram. But if these were all actual pentagons, it would all warp, and there's too much plane. It's hyperbolic. So actually making these things, instead of just looking at diagrams of squished hyperbolic planes, which are what you usually see, these flat embeddings, but you get a completely different understanding and feel and intuition for a thing when you make it for real. So I did. And then, yeah, balloons have this problem where they do that. So, yeah, I don't know. It's also good because it makes for easy cleanup. So I wanted to make it out of something a little more permanent. And I'm thinking, I don't know, what's like a balloon but lasts longer? Probably starts with a B. That would be like balloon. How about beads? So this bead pattern comes from this hyperbolic tiling of 3 heptagons around each point. And so you just put beads where each loop, you loop 7 beads around and connect them all up, 3 at each kind of bead intersection. And you get this bead hyperbolic plane, which, you know, it's all floppy and you can fiddle with it and then like probably destroy it because you fiddled with it too much. And then this one's the same out of plastic beads, and it bends in all sorts of cool ways. So I wanted to make that like big. I'm like, all right, I want like giant beads. So this is a pair of water bottles, cut the bottoms off and stuck them together. Now I have like this big tube bead, and made a bunch of those, and made some polyhedra. So the challenge here was, what can you make, because if you make like a square, that's not really rigid, it'll flop around. So a cube, if you made a cube like this, it would just kind of flop down. But triangles have that wonderful property of being triangles. So these particular shapes made out of triangles hold together really well. And of course, you got to make the hyperbolic plane. And it was just big hyperbolic plane you could flop around. So it was only after making so many hyperbolic planes and kind of getting the feel for what it would be like in 3D space instead of what hyperbolic planes are like when you have equations. I mean, you don't need to see or do anything about a physical hyperbolic plane to do all the mathematics of it. I mean, you've got your equations and your geometry, and it all like works out magically, which is one of the wonderful, beautiful things about mathematics. But after having had all these physical ones, suddenly you start to see them everywhere. And you realize, okay, this piece of dried apple, and you've seen lots of dried chips, dried apples, dried fruit slices. Suddenly, after all of this hyperbolic plane nonsense, you realize, okay, this curves just the way those hyperbolic planes curve. These apples, something hyperbolic is going on here when it dries. Somehow it went from a flat apple slice to these hyperbolic curves. And now the question is, why would fruit do that? How come drying something would change it like fundamentally from a flat Euclidean plane to a hyperbolic plane? Something is going on there, and I want to know what. So these were some results of experiments. People had all these, I don't know, maybe if you took the peel off, maybe it expands more than the center, and that's why, but that wasn't it. Maybe it's the way the cells radiate from the apple that makes the ones inside shrink more than the outer ones, that makes it go hyperbolic, but we tried slicing the other way and it still did it. And then, of course, to test the intuition of hyperbolic planeness, do I really understand it? I did some drawings, some sketches, because then, like, I mean, when you have the physical mathy stuff, if you connect the stuff up the correct way, it makes a hyperbolic plane. You put 7 triangles around each vertex, you get it. I mean, it's going to happen. But to try and draw it the way it would fold around itself and bend and curve, that kind of forces you to look at that and say, am I really thinking about this the right way? Is my intuition for this now better than it was before? So after I drew this, I thought, yeah, this is like ghostly lady dress floating around. And then I wanted to make that. So going on the recycled plastics theme, I cut some heptagons out of grocery bags that I had all stuffed in a closet, and ironed them together, which I don't suggest as a great method of putting together plastic. It was actually pretty difficult. But I ended up with this hyperbolic dress that's made out of just heptagons, 3 around each, and plastic. And it flows around, and then I began thinking about it, like, how about hyperbolic origami? Because flat, plain origami, like, you can do so much with this piece of paper, but the rules here are fundamentally different, and, like, what can you do? So I started with 2 folds. I thought that would maybe be a simple place to start. Oh yay, back to fractals. This is the same Sierpinski's triangle. As I said, you should make it out of anything you have a lot of. So pennies are one of those possibilities. And the 3D version out of balloons, this is a co-author of mine, Mike Naylor, inside this kind of 3D version with tetrahedra instead of triangles. This is more pictures of balloon stuff. We're going to play with balloons later, so I'm going to kind of gloss over this. Yeah, so as you might have noticed, sometimes I like to buy a lot of something from a dollar store and then, I don't know, see what happens. So I was math and musician in residence at Harvard, at Fortseimer House in Harvard, and they have this great dining hall. It's 2 stories, and they have all these students who I was allowed to kind of like force to help me do things if I wanted. And I had these baskets. I'm like, I don't know, we could put them into a dodecahedron, I guess. And we were trying that, and it wasn't working because I had my version with the baskets flipped. They were kind of face open, faced out, and like the angle wasn't right. And when I go into these workshops, I kind of trust the people who are workshopping at me a lot to just help me figure out what to do and bug fix. Like, I don't know exactly what we're going to do with these fly swatters, but we'll come up with something. It'll be cool. So here, he was like, yeah, we'll flip it out, and then it'll work, and it did work. So that was good. And then this also, this is like the section of slides of like how it's good to have people help you and how I'm not like perfect on my own. So this one, right, it was, I had just these kind of blue and green ones. I'm like, yeah, it'll be like an icosahedron, dodecahedron thing. It'll maybe work, but it was too floppy. And then a student suggested, yeah, we'll just take these red ones and put them in between and it'll hold it all. So we added the red ones and it worked. So that was good. And yeah, there it is. We drank coffee under it. I'm thinking maybe it should be called the laundry baskets of Damocles. And here's, I had these plastic dollar swords, and I was thinking of maybe some sort of spirally contraption that wasn't working. So students were like, oh, we'll just make these triangles and then put them together as 5 around, because that's kind of like one corner of a dodecahedron type thing, and it worked. So that was good. And it was very nice, and it made a very nice hat, and made some stuff out of clothes hangers, and oh, this is made out of whisks from another workshop. Its name is Whisk Management. These are some students I trapped in some umbrellas. There's 6 umbrellas that are like the faces of a cube, which, working with the materials, these umbrellas happen to have 8 sides. So thinking 8, all right, that's good for a face of a cube because it's going to work. It's going to have that square face edges. And then we did more stuff. So you have these kind of 8-sided things which kind of can be embedded in a square because an octagon has that nice 4 of the sides are like square sides and then the corners are cut off is a way to think of it. So if you're going to think of a square tiling, you could have kind of a square tiling of the 8-sided umbrellas. And we did that a little. We had all the students take an umbrella and we lined up in a square tiling and we paraded around the dining hall a little. But again, instead of a square tiling that has 4 around, which would be flat for your floor tiles, you could put 5 around, and then it would be too many degrees and it would go hyperbolic. So this hyperbolic umbrella plane ended up, it's got this great negative curvature as it curves from one balcony to another, and then the other curves down across. And of course, I had no idea what to do or where to hang this, and the students were like, yeah, we'll just put it here, and I'll tie the rope on this balcony. So it ended up not being a complete disaster. It ended up awesome, actually. So I didn't really have any idea what I was doing, but it worked out. And then a couple students suggested, all right, now that we got these clear plastic umbrellas, let's grab some whiteboard markers, and we can all use it as a whiteboard space and draw and write poetry, and people wrote little snatches of musical notation, and it was just so cool and not something I ever would have thought of. So I like that project. Here's some pictures from kind of another crazy workshop I did where basically each table got a pile of a different stuff from a dollar store. So this table got a pile of pirate notebooks, and then they had to just, play with it. So we got some cool stuff like that. And another thing was stove liners, which of course got turned into various polyhedra and cut into spirals and all sorts of cool things. Crayon stacks and crayon polyhedra. Barbie dolls was one of the objects. Plastic things and wooden spoons and sponges and protractors and hangers, which turned into something I showed earlier. All right, so I want to talk about music because I am a mathematician. I'm a composer, and all right, here's a part where we're going to have sound. Okay, so one project that I did, this was like years ago, one of the first ones. Using binary numbers in music. Okay, so rhythm is fundamentally a binary thing. If you're using your fly swatters as the drums, right, it's ones and zeros could be like play and rest. And it could be like every one is a note, every zero is a rest. I mean, rhythm is just fundamentally binary. So 0, 0, 0, 1 could be 1, and 0, 0, 1, 0 in binary is 2. And yeah, I just wanted to hit stuff. Who suggested that they were good for drumming? Yeah, it was you. Awesome, I got to do that. Yes. So yeah, these are just the numbers 1 through 8. And now that you can write numbers in binary, basically you can do anything. I mean, numbers using rhythm. And taking a rhythm and then making a melody that uses that rhythm is something composers do all the time. So if you have a very strict rhythm that's based off of a number, and in this case I'm using ASCII code, which means each of these set of 8 numbers represents a letter. And so those are my zeros and ones. That shows where I'm going to have notes. And then as an artist, as a composer, demonstrating rhythm, I can choose what note I want to play. So I'll choose which note, and the numbers will choose when note. All right, so here's an example, and I'm just going to write down the letters played in the violin line as it goes. Each instrument plays its own name. So now you can hide any secret message in music. And if you had heard that and I didn't tell you the secret of the rhythm, you would have never realized that there was secretly words in there. So it's a great method of musical steganography to hide secret messages. So then I decided to change the rule a little. Here I changed the rule that 1 means you start a note. And 0, maybe you keep holding the note. I don't know. If it's a 0, it means you're not starting a note, but 1 is starting a note. And I wanted to kind of create the Fibonacci series in a natural way. And because the Fibonacci series is all about adding. And when you have 2 things added together, well, with music, that could be 2 instruments playing at the same time. So the way this goes is that if the flute is playing, infinity zeros and then 1, and then the violin's playing also 1. And then when they play it once, they're added together into 1, 0, which is 2. And then I'm going to just write how this goes. We should be having sound. Where's my sound? I want sound. Well, it's not feeling like having sound today. You might have to imagine it. No, you don't. Let's go over here, because I was having some trouble with this presentation. I think when I get presentations that are 200 slides long, it starts to have some trouble actually playing them. Here's a Fibonacci sequence in another presentation. Nope. Aha! This is 1. And the other secret in this piece is that if you say C is 1 and D is 2 and E is 3, then every other note in the piano is also Fibonacci. So, it's good to have secrets in your pieces of music, and actually I think a lot of composers do hide a lot of secrets that I think a lot of people don't know about, and sometimes people figure this out. Like Bach and Shostakovich, and I don't know, a lot of composers will use letter names to try and sneak their name into a piece of music. And, you know, I guess Bach needed an H, so he decided this note was H, or I don't know, I guess that was standard practice. And Shostakovich, of course, needed an S, and he used this note. So I was spelling Sasha. This was a piece I wrote for a friend named Sasha. And I could spell S-A-S-H-A. And so now I had these notes, and I had to figure out how to make them sound good. But at the same time, since I was doing this whole binary thing, each measure, each little left-hand rhythm here in the middle is also a letter that also spells Sasha. And so here's S-A-S-H-A. Yeah, I'm not going to go through the whole thing. All right, here's another project. This was for the Math Midway, which is a traveling exhibit of the Museum of Mathematics. And if you haven't heard of MoMath, you should eventually. They're going to be opening in Manhattan in 2012, probably at the end of next year. And it's going to be the best math museum. Right now it's the only math museum in North America, but it's also going to be the best. So this exhibit, what they wanted to have is something to really demonstrate functions. And the idea was they're going to have the organ function grinder, where you stick in a number on one side. You can choose a ticket that you put into this machine. So say your ticket number is 2. So you put your number 2 in, and then you have these knobs. And you can turn these knobs to choose different little functions. So this says double. All right, so 2 times 2 is going to be 4. And then this knob was turned to square. All right, so 4 squared is 16. And then this knob is subtract 3. 16 minus 3. And then out the other side of the machine is going to come 13 on your ticket. And of course you have to crank the handle to make this happen. And you might have goal numbers that you want to get as a result, so you have to choose your functions and your starting ticket carefully. But the question for me was, what's going to play when this happens? What music is going to come out of the machine? And I could have written any kind of function melody, the happy function melody, here's your answer. But I wanted something that did exactly, well, not exactly, but something parallel to what these functions are doing. So what's happening to your number is something that should happen maybe to a melody. So I wrote a little melody for each of the possible input numbers. There were, I think, 64 possibilities, something like that. And so that's, for example, the little melody for 9. And for each function, I chose a function that you do to that melody. Add 3, add 3 half steps to each note. So this note goes up 3 half steps and becomes this note. And then halve, well, that could be having each note value, the length of the note. So this quarter note becomes this 8th note, and this 8th note becomes this 16th note. And then you invert it. Well, an inversion, to do 1 over x, that could be a musical inversion, which is a well-known kind of thing in music function, which is you just turn it upside down. So instead of this melody kind of starting going down here, it starts going up, and it's just upside down. Instead of this down at the end, it's going up. And then, you get 1/6. Ta-da! So, here's 9. Add 3. Halve. Upside down. Ta-da! So obviously this is going to be like tremendous fun for me because I get to write all these cute little melodies. So after that first initial little melody goes in, everything else is algorithmically generated based on the functions. So I get to choose what input melody, and I have to try and choose things that are going to sound good under the transformations. And I kind of know if everything's happy and major, you're not going to have anything too terrible happen. And then there's questions like, all right, there's a square function. What does it mean to take the square of a melody? I don't know. You can interpret that tons of ways. I just decided that if this is 9, we add a harmony on top. And just to make it sound a little more different, it also changes from major to minor or vice versa. And then the square root instead puts a harmony below it. And those harmonies are also algorithmically generated based on what chord it is. It'll just take the next chord member up, which for such simple melodies, usually makes something palatable. All right, here's some more examples. 7, subtract 3, square root, double. All right, and here's square root 2. Oops, I accidentally pressed something. Yeah. So one of the things this machine can do is, because you can get negative numbers and it has a square root function, you can get imaginary numbers. And I didn't have to do anything special for this, but you kind of want to, right? So what would it sound like for a number to go imaginary? And here's what I decided to do. So here's the Happy 64 melody. Now it's upside down. Now this is a negative number. Let's take the square root. Yeah, so it moves the notes up 2 octave and it shifts them into another scale all automatically. You can imaginarize any melody you want. Imaginize? I'll have to think about that one. All right, but here's the other problem. When you're having a museum exhibit, especially, there's going to be a lot of kids in this museum, and kids tend to, play with stuff, and, they can be a little rough, and they tend to break things. When you have a group of students, you know that one of them is going to try and divide by 0 and break your machine, because that's just what they do. It's their nature. They're destructive. So, unfortunately, here's a case where that happened. Not every exhibit can be a winner, so anyway, that was a shame, so let's just not think about that anymore and move on to the next project. Oh, right. Here's where I want to switch back, because I changed the order of things because I want to play with freeze patterns. So what did I do? All right, yeah, music boxes. So I got this this music box thing that plays a paper tape, and you punch holes in this kind of paper tape, and you send it through, you turn the crank, and the music box will play based on what holes you punched in there. And I was like, this is awesome. You put the paper through, and it plays it. Obviously, when you have a strip of paper, you probably want to make a Mobius strip and put that through the music box. So let's see if this video works. Yes. So that was fun, but I want to do more stuff with these awesome music boxes. And well, you have this strip of paper. You can put it through different ways. But you could also put through more than one music box at once if you wanted. And, you know, one would just play the same thing the old one did later, and that's a musical structure called a canon. And what better example, hey, where's my canon? I think I have to switch over here again. What better example than Pachelbel's canon, which people tend to know. Yeah. So we tried that. So the repeating bass line is a loop, and all right, that's enough of that. But the whole thing is online if you want to see. This was a collaboration. I wrote the music to this. And then these are Eric and Marty. This is Martin Domain, who was like, yeah, I'm going to blow glass blindfolded. It'll be great. Oh, but there's symmetry in the music. That's... Yeah, so that's kind of what happens when you start combining math and art and music and mathematical paper folding and mathematical music making. So that was fun. Wait, but that's the end of that presentation, but that's why we're switching back to this one, where we're moving on to symmetry stuff. Okay, I don't know where we are. Here we are. All right, so here's the part where we're going to think about freeze patterns. Music can have symmetry. You can, here's the inversion we were talking about before where, oops, I forgot to turn on my pen. All right, so we have this motive that, goes up, but you can take any melody and just flip it upside down. So here's this kind of reflection line, and here's the inversion. If you play something backwards, that's a horizontal reflection. And yeah. And then, of course, you can play it both backwards and upside down. That's like a 180-degree rotation. That's called the retrograde inversion. So these transformations are really common in music. It's like Music 101. You learn all about these symmetries, and you find them in music everywhere, and composers use them all the time. But But then there's freeze patterns. Now freeze patterns are repeating patterns that repeat in one dimension, and they can also have other symmetries. And there's some different combinations of symmetries that they can have. For example, this is called a dizzy sidle. We'll show that more in a moment. But it's got this vertical mirror line here, and it's got points of rotation here. Right, and it's got kind of, this particular one has this kind of sine wave shape, and you hear these kind of arpeggiating melodies often in music where they're, going up and down. And if you flip it around that point of rotation, the music is exactly the same. It still follows along that red line. And there's 7 types of these. And, all right, I'm going to show some slides too, and then we'll start playing with paper. 7 types of these in music and in normal music, and you find these in architecture, you find these in nature, you find there's a lot of these patterns out there. So these are natural to music, because repetition happens in music all the time. You get repeating arpeggios, repeating bass lines, just repeating melodies, and these kind of symmetries are common in music, right? You play on the violin, you go up an arpeggio, and then you go back down those same notes, and that's like a vertical mirror line. You're playing something forward and then backwards. And so these things exist in music. Composers use them all the time without realizing, oh, this is a mathematical freeze pattern that has these symmetry patterns, and there's 7 of them. But for example, Debussy's 3 Nocturnes, he uses all 7 freeze patterns. Like, I'm sure he wasn't thinking about it, but he used them just by accident because, I don't know, Debussy does that kind of thing. And I wanted to do this on purpose. So, and to keep the art in it, I mean, you could just have repeating notes that repeat forever, and, that would be nice. It would be fun. But I wanted to more use it as inspiration and then break away from the strict symmetry. And should music be playing? All right. And then there's wallpaper patterns, which are basically the 2D version that go in 2 dimensions instead. But I'm going to be tired of these slides. Let's turn the lights back on and play with some paper. And this slideshow is not cooperating with me. Okay. So the first thing I want to play with is just some basic symmetry. So you should have a couple copies of this, and you can kind of separate it into these different little kind of roundy symmetric things. Just, cut them apart, because not everyone needs to do everything on the whole sheet, because there's a lot of them. And what I want to think about basically is orbifolds, and what symmetry really is and what it really means. Here, I can get a copy of that up here. So for example, you've got your simplest little foot here. All right, so the game we're going to play, the goal, is going to be to fold or do whatever it takes to each of these little things to get all the feet to lie on top of each other. So what symmetry is about is equivalency. It's saying that these points are equivalent. Now where's my little foldy guy? All right. So for example, here's the simplest one, the circled one. And it's got this line of symmetry right down the middle. It's got a mirror line. And the game is to figure out how to get these feet to be like in the same space, and you have to pretend you've got infinitely thin paper, and that if you fold this in half, the 2 feet are directly on top of each other, and you win. This is, the easiest level. And the way to think about if you know you've won or not, you think, if I cut out this piece of paper, folded how it is, and I cut out this foot, would I be cutting out exactly this foot and only this foot? And if I opened it up, I would just see the piece of paper minus the foot and have, little foot pieces on the ground. So for some of these, you've got, what's this guy? If you cut out this one, there are a bunch of mirror lines, and you have to fold along all of them. And you should end up with just one foot cut out to do that cuts at all the feet. All right. So can I stop you all for a moment? And I'd like to ask, all right, so I assume that everyone who chose this one, who got this one? Hold it up if you did that one. Bottom right. All right. You got it. We have some winners. All right, this is, here's another one. Anyone have that one? Right, we got that one. All right, how about this one? The bottom middle. Does anyone have any clue how to do this one? Down in the middle. Are some people having trouble with certain ones on this sheet? Yeah.
I have them on top of each other, but they're not directly on. There's a random foot in between.
A random foot in between. The name of the game is if you cut out the foot, you just need to cut all the way through your folded paper. You should unfold it to get exactly what it is. So if there's a random foot in between, I don't think that works. No, you can't have paper between the two. Because if... No extra paper. So everything that's on top of itself should be completely equivalent. Right? We're getting back to equivalency. So,
Have 6 make it to 3. Do you want them 3 on top of each other?
it should be all on top of each other.
So I could
but
just
here a problem is there's this blank paper in between. So everything on top of itself in one layer should be equivalent. But this blank part is not equivalent to the foot part. Yeah.
So no blank paper.
Yeah. All right. I'm going to give some hints. So all the paper that's grouped together on top of itself is going to be equivalent, and we're going to pretend that it's all flat together in a two-dimensional surface with no thickness. So when you have something like this, and it was kind of evil of me to have you start thinking about this, but you've got this 2 feet and you've got this point of rotation. And you want these 2 feet to be on top of each other. And I can do anything as long as in the end everything is going to be, all the paper's still connected where it should be connected, and it's all equivalent. So if I were allowed to cut just temporarily, I mean, if I just rip this in half and I put it back together later in the end, that would be allowed because in the end, you know, these points connect the way they should. But if I were allowed to do that, how would I get these to be on top of each other? Right, then obviously you could just rotate it and put them there. But then you've got this problem where, I mean, you've got these hanging edges, and really this edge belongs along, well, you can just kind of see, you've got I'm going to use this Sharpie. So it's okay to rip, but in the end, this is going to have to connect to there. And at the bottom, we've got I don't know, let's put a little circle. This circle should connect. So when I go like this, how would I get those to connect? What could I do to this to get, we got the little line back here that needs to connect to the line here, and the little circle up here that needs to connect to the circle that's down here. Curve it around. Oh, I see. You're making a pivot point or a cone point. Yeah, so if I just cone this around and connected those, and you know, one's in front and one's in back, but as soon as they're on top of each other, we're pretending that it's equivalent, they're the same. So now this little cone point is basically the essence of a 360-degree rotation. And anything that has, you know, 360-degree rotation symmetry, if you kind of wrap it around, you only really need to make one slit in it. You can wrap it around until the 2 edges meet. And if everything meets up how it should, everything, even if, you know, it's at one side of the layer or the other side of the layer, because remember, we're pretending that these layers are now all the same equivalent thing. And now these feet are equivalent. We're basically saying, all right, with this cone point, we're going to make these equivalent feet. So now see if you can get some of the other ones that have more than 2 feet and what happens with them. Did that make any sense? All right. So do we need any ideas?
So I get the fact that they have a piece of paper in between, so I'm trying to figure out what you did to get that cone point.
Right. So you can cut it up as long as you put all the edges back together in the end.
Okay.
That might help. What's going on over here?
We don't understand what you're talking about when you say cone.
Good, because here I am to tell you.
I have this, right?
Right.
And we fold it like that, and then we have them on top of each other.
The feet are, but you've also got this other paper in between.
Right.
So by putting it together, you're saying all this is equivalent in this pile. But clearly this is not equivalent to this, because this is a foot, and this is not a foot.
True. There's no foot there.
There is no foot there.
No, so you have to make it.
Well, you can cut as long as you put it back together in the end. So in this case, I cut, I stacked, and then put these edges back together where they should go, and now they're all connected.
So
Even though they're kind of out of order.
So you do it outwards, but then this has.
It does. So if you need to cut it apart, you can, but first you can try it with this. Ooh, already moving on to freeze patterns.
I don't know what that means, but yes, that's what I'm doing.
Did you conquer all of the cone points?
Which ones? No, I haven't even tried.
Yeah.
I'm just trying to.
Like I could hear you, but not hear you.
Right. I should probably explain again because I think a lot of people didn't hear me. That's a good point. Oh. All right, I'm going to demonstrate some things. Oh, I don't think I have scissors. All right, scissors. All right, so for the 4-way one, this has this 4-way rotation. And what the essence of a 4-way rotation, and if I was embedded in 4 dimensions, I could do this without cutting. I would just be able to like warp this in a rotational loop and everything would work. I think you could do that in 4 dimensions. I'm pretty sure, yeah. But because I only have 3, I'm going to have to make this cut. And by rotating this around, and the number of point of rotational symmetry, what do you call that? The number of rotational symmetries, whatever it is, you're going to have to turn around a certain number of degrees. And in the end, I turn this around, I flip it around, and eventually all the feet are on top of each other, and I've got this cone. And depending how much I have to spin it around, the pointier this cone is going to get. So when you've got the one that has a ton of feet around, you're going to have to get a really skinny cone, whereas if there's only 2 feet around, you get a different angle of cone. And the shape, what you end up with, and this is kind of the point, what you end up with says something fundamental about the symmetry, or rather it is the essence of what a symmetry group is. Because this cone, if you're thinking about all this paper being the same thing, and maybe it goes infinitely, this cone, and it comes to this one cone point, that is what a 4-way rotation is this cone. And all you need to do is have this cone, and if you have this cone, and you cut something in it, let me make sure my ends line up, because the end of one paper here should be in the same spot as the other end that's in there, and if they're in the same spot, then they're nice and equivalent. So if I cut something in this cone, I'm just going to kind of stab into it. and then unroll it, it should have the correct symmetry. Because I'm only cutting one thing, and then I unroll it into this really ugly thing that's kind of all over the place. Nope, I didn't roll it enough. But this one I did earlier, right? You have 3 around, you make it into a cone. If you cut something in that and then unroll it, it will be something you cut with rotational symmetry, which is very different from like if you fold a snowflake. Basically what that is you're getting like the essence of what 6-fold symmetry is in your little snowflake triangle, and then you cut your things in it. And then when you unfold it, you have your snowflake or your foot flake. It's kind of gross sounding. But, you know, the symmetry happens because of the shape it was folded into. All right, I want to do freeze patterns. I just want to get over the cone point trick because it's useful for maybe a couple of the freeze patterns. So there's 7 of the freeze patterns, and what they are, first they have to repeat infinitely. So you have anything that repeats infinitely, you can put it into one of 7 categories. This first one just plain old repeats. And if you cut out that strip of paper, you can figure out how would you fold it, how would you do something to it that would make it so that all the paper on top of itself is equivalent. And if you cut anything out of it, you could unroll it into a repeating pattern. The second one, this is called the hop. John Conway's notation, he named them all after like foot things you do, which means that if you've got snow or mud or sand, you can do these and leave footprints in each of the 7 freeze patterns. But so this one's called the step, and it follows a glide reflection, right? You've got the right foot and then the left foot and then the right foot, and then the left foot is up above there. This one is called the jump, and it repeats, but it also has this line of symmetry. So each of those, there is a way to fold that physical piece of paper or do whatever else to it to get what's called the orbifold, and that's the fundamental shape that belongs to this freeze pattern, that anything you have on that shape can be represented by a repeating pattern. And yeah, like this one has these horizontal lines of symmetry, and this one's got points of rotation, and this one has both horizontal, and anything else you come up with is going to fall into one of these categories. And the second page, which has kind of trickier patterns, they'll also fall into one of the 7 categories, but it's not necessarily going to be a 1-to-1 foot correspondence. There might be more than 1 foot in each kind of unit of repeating, or not. But each of these is also going to be one of those freeze patterns. But it's not like there's anything fundamental that it's a foot. It's just a way to help you think about the right and leftness of it. So you can try and figure out what here would have the same kind of orbifold, how it would fold to become something. It'll look like the same thing that one of these will. So for a simple example, I should be playing with stuff. Yeah. All right, start playing with stuff.
Because there are
How you doing?
horizontal reflections, vertical reflections, and rotations. And I have talked about you have to do all 4.
All right. Do you get the idea? Or if you get the idea well enough that you're ready to start playing, then that's good.
What are we attempting to do here?
Get all the feet to line up with each other. It's the same challenge, but now you have to pretend you're doing it infinitely. Yeah, that was this one. You win. Yep.
So these are the hard ones.
Some of the other in that category are hard. These are maybe less possible to fold. It's more about what are these patterns? Which of the 7 would they be? But you should try some of the other the other ones that have more room and space to play.
The goal is still 1 foot on.
Yeah,
Can I cut
everything.
paper to get rid of so I can see? Can I get rid of that paper?
If you add it back in the end, it has to go exactly where it was. You can rotate. You can make a cone point. Yeah.
Because I can't tell them.
Are you?
You had it. I am doing my.
You have to score them.
Any confusions?
I don't know. Is this right? Did you just roll it?
Is it right for what? How do you? Yeah, that works.
Okay.
Yeah, what's wrong with that?
I don't know. I just rolled
Nothing.
it.
It's great. Yeah. Some people get that very quickly, and some people it takes a long time to realize that rolling
How's
is.
the paper in between?
No paper in between. Because the paper in between is not equivalent to the other things in the thing. Any questions? How we doing?
So my question is, why are there just 7?
Why are there just 7? Can you think of anything that would be different?
I'm thinking that. What do you mean by different?
Well, that would be an 8th.
Well, I'm not exactly sure what my constraints are yet. That's why I'm not sure why there's 7. So,
Well, it has to repeat infinitely, and it can have other symmetries.
2-dimensional.
Yep.
Hi.
Yeah?
Have you heard, I'm sure you have, I'm just asking because I'm a scientist. So are you connected to protein folding?
I don't connect this to protein folding, but actually a lot of people who are into folding are also working on protein folding. So I don't know if
fold proteins?
freeze patterns specifically are related to protein, but definitely, yeah, how things fold and what the capabilities of. Is that like a particular protein fold?
It's just like I don't know if it's a particular protein, but when proteins fold, they look like sulfur bonds, and sometimes they're hidden under those loops. So you have to, it's like matching toes, I guess if you want to say bonds. So if you want to loop back up and around and find that sulfur that you have to bond with, then you have to tuck up underneath and find it. So you end up with a lot of shapes like this in protein when you get to those
Cool.
tertiary and quaternary levels.
Yeah, I haven't looked much at protein folding. I know other people who are more into that.
It's just interesting because
It's one of like the big open folding problems that. Neat. Good.
here we go.
I like your hat.
I think so.
There are also 2 bonus sheets. If you think you've got a handle on how to fold freeze patterns, you can try. There are a couple wallpaper patterns, and both of these you can fold into their orb fold, and then you can like cut it and unfold it, and you'll get like a paper pattern if you want. Or like this one can be folded and then folded if you want to cut like a snowflake. You can actually fold orbifolds of wallpaper patterns, and then snip them up and then unfold them into things. So that's the bonus, is to try and get this one. Or this is the one here. How would you fold this in the same constraints?
And then I had to tuck it
to break and tell people to get food while they...
Yeah,
chat?
I think that's already happening, so
Yeah.
that's what I've been doing back here.
Oh, good.
And I checked over there. We can go over there and use the big space there.
Oh,
If you want
excellent.
to do that. See, the cameraman's going to want to get set up, so if we'll just,
Yeah.
when it's time to break here, we'll go over there, okay?
All right. All right. So now is also when you should eat some food. It's, I don't know, hang out, eat some food.